Somebody just pointed out that the calendar on Canvas is incorrect. I'll have to make that correction. I don't know if it affects the next exam date, so that's something you probably want to take a look at. All right, so what we're going to do today is take a look at some system analysis using the frequency response. We did not have a meeting on Friday, so I had asked you to review a couple of Panopto lectures looking at stability margins. So we're going to look at it again today. We're going to take a look at stability margins. We're going to practice looking at stability margins on the Bode diagram, and also take a look at the effect of what we'll call proportional control. Okay. So let me sketch the control system that we're looking at. And what we have right now is we're going to try looking at a system where we're using proportional control. Proportional control means that the controller can be just modeled by some gain, K, like this. And then we have the plant, the process that we're trying to control. And this is the feedback path. And we're given information. The frequency response is given for just this part. Okay, so we know the frequency response of the process, and we want to know what is the behavior of the control system. So that's what we're going to do. We're going to analyze the stability and maybe also take a look at some other things. So we're going to look at practicing some analysis of that. So I want to emphasize that what is given is the information in the shaded box. Okay, we know information about the plant, but we want to know if the feedback system, if the control system is going to have nice behavior. Okay, so what I've handed out are some frequency response plots. We're going to start off with the frequency response plots shown in the solid lines. Okay, so these are Bode diagrams. And so the Bode diagrams, you see, we're going to start off with, we're going to look at this solid curve, and we're going to look at this solid curve. And notice how the curves have been labeled: magnitude versus frequency, and phase versus frequency. All right. So let's take a look at some properties, some questions that we can answer just by looking at the frequency response. So some things we can determine. Okay. We want to determine some things. Let's take a look at, for example, let's take a look at the system type. Okay. The type is the number of number of 1 over S terms in the open loop. So whenever people talk about control systems type, we have to take a look at the open loop. We look at the open loop model and determine the system type. So right now the open loop model is K times the plant model. Of course, I don't give you the transfer function. I don't have the transfer function. I just have the frequency response. Okay, so it's the K and the plant. So it's just this part. Well, K doesn't have any 1 over S terms, so the question is, does the plant have any 1 over S terms? So let's take a look at this thing. Let's take a look at this curve, and let's take a look at this curve. And we want to decide, what do we know about the frequency response? What should the frequency response look like if there are 1 over S terms? Okay. So looking at this response, one of the things that I see is that in the magnitude plot, the low frequency slope is 0 dB per decade. Okay, let's take a look at this thing. I'm saying this slope is flat. Okay. In the phase plot, the low frequency phase is, let's take a look at the phase. At low frequencies, the phase is 0 degrees. Okay. So these two things together would suggest to me that the number of 1 over s terms is any suggestions? 0. Okay. If I had a 1 over s term, the initial phase would be like minus 90 degrees, and the initial slope would not be flat. Okay, there are not any 1 over s factors. So the conclusion is it is type 0. Okay, the type is equal to 0. That's the system type. Okay, let's take a look at the relative degree. Relative degree is number of poles minus the number of zeros. Okay, the number of poles minus the number of zeros. And we can determine this by taking a look at the high frequency behavior. Let's study the high frequency characteristics. In the magnitude plot, the slope is, let's take a look at our magnitude plot. Let's take a look at this slope. Okay. Here's one decade, and it looks like in 1 decade it's dropped approximately 60 dB per decade. Okay. In the phase plot, phase is, let's take a look at the high frequency phase. At high frequencies, looks like the phase is approaching some multiple of negative 90 degrees. It looks like it is approaching minus 270 degrees. So we can guess that the relative degree what would be the relative degree? Any suggestions? What would cause the slope ultimately to be 60 dB per decade, minus 60 dB per decade? 3? Very good. Okay. So it appears to be a type 0 system. Relative degree is 3. Let's see what else we could determine. Can we determine the DC gain? DC gain says we need to look at the gain curve. Where's omega equal to 0? 1, 1, 1, 0.1, 0.01. 0.001, 0.0001. So 0 is over here somewhere. So what am I going to do with this data? What would be a reasonable assumption? Extrapolate, right? Let's assume that it doesn't change. So let's assume DC gain let's study the gain at low frequency. Let's study the gain at low frequency. And since omega equal to 0 is not on the curve, we need to extrapolate. And so reading this curve right there, I get 20 dB, which if I convert out of dB, what is that number? What is the gain? 20 dB is equivalent to a gain of 1, 10, yeah, 10 to the 1, so it's gain of 10. Okay, let's suppose that I do give you some additional information. We are told the plant is stable. Okay, we are told the plant is stable. Is the control system stable? Okay, we're told that the plant is stable. So we're given the frequency response of the plant. And the picture that we're dealing with is this picture. And the question is this thing going to be stable? So what we'll do is let's study the stability margins. So there are 4 words that we need to review. Gain margin and phase margin. We need to measure the gain margin at what is known as the phase crossover. We need to measure the phase margin and what is known as the gain crossover. Okay? Do not confuse things and say, I measure the gain margin at the gain crossover. Nor do you say the phase margin is measured at the phase crossover. No. The pairing goes like this. Okay? Gain margin measured at the phase crossover. Phase margin measured at the gain crossover. 4 numbers that we want to be able to read on the Bode diagram and on the Nyquist plot. And that was kind of the review on Friday. So let's take a look at this. Let's find the phase crossover. Okay. So phase crossover is where the phase, this is the phase, crosses over a particular line. See all these horizontal lines? It's got to cross over 180. So we had to take a look at this diagram and figure out where is 180. So here's 150, here's 200. That's a total of 50 degrees. So 180 is probably somewhere about, maybe about like this maybe. Okay. Got to eyeball it and figure out where's 180. So we'll cross and we'll come over here and we'll say maybe it crosses over right about here. Okay. We'll label that PC. Okay. PC does not stand for political correctness. It does not stand for personal computer. It means I love to watch British TV. It is not police constable. Okay? What else could PC stand for? Polarity change. Okay. PC is phase crossover. So what is the phase crossover? We read it like this. Okay. 10 to the 1 is 10, right? So this must be 11, right? Wrong. This is not 11. What is this? This is 20. So again, we got to sit here and eyeball this and figure out what that might be. And of course, this is a nonlinear scale. It's a log scale. All right. So what we're going to say, phase crossover. Right now we're reading it. It's approximately, I'm going to say today, I'm going to say 12. With units that we read off this frequency scale, we read off the scale, it's radians per second. So let's just say it's 12 radians per second. Okay. Now what we do is we extend this curve, this dashed line, up into the phase plot. So let's go up. We read the gain margin at the phase crossover. So here's the phase crossover. In the phase, we have found the phase crossover, but now we need to read the gain margin, which means we need to get into the gain plot. So we extend this up. And we see the gain. And then we take a look at the difference between what the actual gain is and 0 dB. Okay. And if you use the margin command in MATLAB to do this, it's going to do something very similar to this. It's going to draw a vertical line faintly to identify where the phase crossover is. And then it's going to draw kind of a heavier line, a colored section, to show you graphically the gain margin. Okay, now the gain margin is always measured from the current gain to 0 dB. So draw an arrow from the current gain to 0 dB, which means the arrow goes this way, which means this is a positive gain margin. And so we measure that height using our scale right here. And we get here that the gain margin at 12 radians per second, this is approximately 10 dB. Okay, a positive 10 dB. Okay, any questions about how to measure the gain margin at the phase crossover? All right. Now the next thing we want to practice is measuring the phase margin at the gain crossover. Phase margin at the gain crossover. So we find the gain crossover. That means that's where the gain crosses over a important line, and that is 0 dB. So here's 0 dB. We've got to see where this crosses 0 dB, and it happens right here. So right here, that's GC, gain crossover. Okay. So the gain crossover, again, we read the scales, come down here, right there. That looks like 10, 9, 8, 7. Seven radians per second. And now we drop this line down into the phase. Okay, MATLAB's going to do something very similar for us. 10, 9, 8, 7. Let me be sure I'm on the right dashed line. There it is. We hit the phase curve. And then what we want to do is, this is the phase margin. Now, by convention, to determine the gain margin, we go from the current gain to 0 dB. We go from the current gain to 0 dB. But the phase margin is done opposite. We measure how far we are from 180. So we go from 180 and we draw an arrow like this. Okay? We measure how far we are from 180 degrees. So again, this is a positive margin. So we'll have to eyeball that and figure out what that is. That looks like it's about 30 degrees. This is a positive 30-degree margin. Okay. If you didn't catch that from the notes, I'm going to say it again. If you didn't catch it from the Friday notes, I'm going to say it again. Gain margin is measured from the current gain to 0 dB. That's the direction you need to draw your arrow, from the current gain to 0 dB. Now you would think we would be consistent with the phase and do phase margin from the current phase to 180, but no, we don't. Phase margin, by convention, is measured from 180 degrees to the current phase. Okay? So this is important. If you don't get this, you don't remember this, you will get the wrong sign on your margins. Okay, so we have on this picture now done manually what MATLAB would do. If you gave it a model, if you knew the transfer function, you would enter the model and ask it to use the margin command, and it will draw these lines for you, and it will tell you up at the top the same information that we have just written on this piece of paper about the different margins. Let's also, real quickly here, let's kind of sketch what's going on in the Nyquist plot. Okay. The Nyquist plot, we're going to label this as the real axis and the imaginary axis, or we're going to think of this as polar coordinates. We're going to call this 0 degrees, minus 90 degrees, minus 180 degrees, minus 270 degrees. And the distance from the origin is the magnitude. Now, studying my plots, magnitude and phase, I see that at low frequency I have a gain of 20 dB at 0 degrees, and we say that that is equal to 10. This is 10 at an angle of 0 degrees. That's at low frequencies. And as frequency increases, my gain gets smaller and smaller and smaller, which means I need to approach, in the polar plot, I need to get closer to the origin. But I need to approach it from the minus 270 degree direction. So I need to draw a picture that looks something like this. So here's the Bode plot information. This curve corresponds to these two curves in the Bode plot. Okay, two curves in the Bode plot correspond to this single curve in the Nyquist plot. Now, the complete Nyquist plot would have the negative frequencies, which we have to add in. And we know that the negative frequencies just produce the complex conjugate curve, and so it looks something like this. It should be symmetrical. Now, what we know from this plot is that when the curve crosses 180 degrees, when this curve crosses 180 degrees, this is the phase crossover. phase crossover is here. And the phase crossover, at the phase crossover, the gain was minus 10 dB. Minus 10 dB is less than 1. So that means 1 must be out here. Negative 1 must be out here. 1 corresponds to 0 dB. But we're 10 dB below that, which is probably about 1/3, I think. My scale is probably not real good. So that's like this. Okay. Any questions about how I decided that minus 1 must be out here? Minus 1 must be out here. I look at that from the Bode diagram because I see at the phase crossover, my gain is below 1. Another way to look at it is say the gain crossover. When the gain crossover is crossing 0 dB, what is my phase? My phase is not quite 180 degrees yet. So if I were to sketch this in the Nyquist plot, let's do that real quickly. To determine the gain crossover, I got to draw a circle of radius 1. So I do this. I kind of sketch a unit circle like this. This is 0 dB. I cross 0 dB right here. So this is the gain crossover. And I measure this angle. I measure this angle for the phase margin. And which way do I draw the arrow? Yes?
Did you say negative 180 degrees the gain was positive and not
Did I say, what did I say? Did I say that the gain was negative 10? Where did I, it should be, no, at 180 degrees, it's negative 10 dB. Negative 10 dB, not negative 10. Negative 10 dB, yeah. Negative 10 dB, you have to convert that out of gain because the Nyquist plot is not in dB. Does that answer your question? Okay. Whew. Thought I really messed up. Okay, remember the phase margin is measured from 180 to the current phase. The phase is right here. And so draw the arrow this way. And so this should be, it's supposed to be 30 degrees, but doesn't look like 30 degrees. It's because this is a terrible sketch. Okay, so we practiced looking at the margins in the Nyquist plot and the phase Bode plot. But we still are trying to answer this question. Is the control system stable? We've analyzed the stability margins, but let's take a look in the Nyquist plot. In the Nyquist plot, let's apply the Nyquist. Let's apply the Nyquist stability criterion. So I have to do what? P, n clockwise, add them up to get z. Okay. What is P? P is the number of poles, open loop poles in the right half plane. Open loop poles in the right half plane. How many open loop poles do I have in the right half plane? Okay, we're told the plant is stable, so P is equal to 0. And in the clockwise manner, what is n? These are the number of encirclements of minus 1. The number of encirclements of the point minus 1. Here's my terrible sketch. Here's minus 1. Here's the curve. And it doesn't encircle it at all, so n is equal to 0. I add all that together, I get z is equal to 0. What is z? Z is the number of control system which implies closed loop poles in the right half plane. 0. So that means the system is stable. Okay? That means the system is stable. So back to our question. We're told the system is stable. Is the control system stable? We look at the stability margins in the Bode plot. We could sketch the Nyquist plot and use that same information. Let's go back to the Nyquist plot, the Bode plot, and take a look at this information again. And our conclusion is that the control system is stable. Now, I'd like you to take an observation. Notice where the gain crossover is. We've got two vertical lines. This one is the gain crossover, and this one is the phase crossover. Okay. So the conclusion we can make is, we can make a conclusion that one of the carryways that control systems engineers know, they can look at a Bode plot real quickly and determine whether or not the control system is stable. They don't have to sketch the Nyquist plot like we just did. So here's a tidbit, a conclusion. If the plant is stable, and this is a conclusion that only works if the plant is stable. Okay, use this tidbit only if the plant is stable. The conclusion is the control system is stable double arrow, if, double arrow means if and only if, gain crossover is less than the phase crossover. Okay. Don't use this conclusion, don't use this theorem, don't use this observation if the plant is unstable. Okay. If the plant is stable, then we can conclude that the control system will also be stable if and only if the gain crossover is less than the phase crossover. That's what we have in our plot. Gain crossover is less than the phase crossover. Okay, let's do some more analysis today. What is the steady state error for a step input? What is the steady state error for a step input? That means we're looking at this signal right there. Okay. We have our plant. We have this. What is the steady state error for step input? Well, we've already determined this is a type 0. Since it's type 0, we remember there's a formula that says that E steady state is 1 over 1 plus the proportional error coefficient. Position error coefficient. Yeah, position error coefficient. Today, Kp means position error coefficient. Sometimes P stands for proportional or something else. It's the position error coefficient. And remember, we get Kp is equal to, we take the limit as s goes to 0 of g of s. If we know the transfer function, we let s go to 0, and that's Kp. This is the same thing as the DC gain. Now today I don't have g of s. I never wrote down a g of s. I don't know what the transfer function is. I only have a measurement. But we looked at the frequency response. We extrapolated, we estimated the DC gain is equal to 10. We got that by looking at the low frequency curve, and so we saw there's 20 dB. 20 dB is a gain of 10. So our conclusion is that E steady state is on the order of 1 over 11. Okay. Okay. Any questions about steady state error? Okay, we got that. We can determine a lot of information about control system behavior by looking at open loop behavior in the frequency response. Okay, how can we reduce the error? How can we reduce steady state error? Our control system now is this. Okay. Many times in life, we don't get the luxury of doing anything about this. Okay? You're the new engineer. They say, go out and tune that thing. Well, they're not going to give you enough tools to change the plant. Okay? We've invested millions of dollars into this plant. We're not going to change it. Okay? Word of advice to you young men, after you get married, don't try to change your wife. You can change. Okay? All right, so what we can do is increase K. Increase the loop gain. Okay. So let's say, and this is what's happened, we can make error 10 times smaller. Instead of 1 over 11, we can make it 1 over 100 or 1 over 110. Okay? Make error 10 times smaller by choosing K equal to 10. K equal to 10 is what in dB? What value is this in dB? Let's see, log of 10 is 1 times 20, that's 20 dB. Okay. So what is the effect in the Bode plot? Okay, so let's study effect in the Bode plot. Okay, study of the effect in the Bode plot. What we should see is that the gain curve is adjusted. We need to adjust the gain curve. Since I'm just changing the gain, what is the gain? What is the phase of this? What is the phase of 10? What is the phase of 10? 0. Okay, in polar coordinates or in phasor coordinates, this is going to be 10 at an angle of 0 degrees. So the phase curve is unchanged. Okay. Gain curve is adjusted upward. So this is what we have in this plot, the dash curve. I've increased the gain 20 dB. K is equal to 10. 10 is the same thing as 20 dB. I've taken this entire curve and shifted it up. Now there's an optical illusion. It looks like it's closer here than it is here, but actually if you measure very carefully, you'll see that here there's a 20 dB increase. At every frequency point, this dash curve is 20 dB higher than the solid curve. Okay, so in the time remaining, let's examine the new stability margins. I want to find the phase crossover, the gain crossover, the gain margin, and the phase margin. 4 words. Okay. Okay, what is the phase crossover? Well, since we didn't change the phase, it's unchanged. It's unchanged. The phase curve didn't change. So the phase crossover is still here. However, the gain margin is now changed. Because I extend this line up, I go all the way up to the gain, and now I draw a line from the current gain to 0 dB. And so now this is the new gain margin. Here, this was the old gain margin. So the new gain margin is now negative 10 dB. Notice the sign change. It was 10 dB, and now it's negative 10 dB. Okay. Remember, gain margin is measured at the phase crossover. Put these two together. Let's take a look at the gain crossover. Where does the gain, the adjusted gain, cross 0 dB? It's out here now. And we have to read this. This is 10, so that means this is 11, right? Wrong. Gain crossover is now at 20 radians per second. And now we drop down into the phase. We hit the phase curve here. We draw the new phase margin like this. We go from 180 to the phase, and so now we see the arrows change directions, and this is the new phase margin. This was the old phase margin. And I'm going to say that looks like roughly whatever minus 30 degrees. The old margin was about positive 30 degrees, and I'm eyeballing saying that looks roughly the same length as that, so it's probably about 30 degrees. Okay. More importantly, the phase crossover is here, and now here's the new gain crossover. And what I have now is that the gain crossover is greater than the phase crossover. One of our earlier tidbits says that the control system is stable if and only if the gain crossover is less than the phase crossover. But now I've got the gain crossover is greater than the phase crossover. And my conclusion is that the system has become unstable. All right, so what we've attempted today is to try to reduce the steady state error of a control system by increasing the gain, and by studying the stability margins, we discovered that this is not going to work. So what we're going to do in the coming days is we're going to say, is there a way for us to reshape the plots? That's what frequency response design is. We like this. At low frequency, we've increased the gain by a factor of 10. We've increased it by 20 dB. That's a good thing. We don't like this. So what we want to do is reshape the curves so that we can preserve stability over here. So that's the idea. All right? Proportional control just simply shifts the curve up. We're going to look at some compensators that allow us to change the shape of the curves. Okay. Have a good day.